Hello, this is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Functions and Mathematical Modeling. One of the important aspects of this course is that we really are going to be doing real-world problems. We'll talk about these kind of things, and the way we will approach this is by using a process called mathematical modeling. We start with a real-world problem, and we create a mathematical model or formulate a mathematical model. We then use mathematical techniques we will discuss in the course to solve that mathematical model. So we have a solution to the mathematical model. We will interpret that solution in terms of the real-world problem, and we really should test to see if it is useful in the real world. One of the techniques we're going to be using is curve fitting. Curve fitting is used in many examples in this course. We find the best red curve to approximate the noisy black data. So here's the noisy black data, and here is the red curve that we will find. This is a topic we will discuss in considerable detail later in this course, how you do that. But for now, just know it can be done, and this has been done in the examples we discuss. So here is the first example about bounced check charges. So overdraft fees have become an important piece of a bank's total fee income. And so here is, based on years, from 2004, so 0 corresponds to 2004, and 5 corresponds to 2009. And these are the overdraft fees in billions of dollars. Now, the curve that models this, when you do the curve fitting, is this one. Y equals f of t equals this, and such functions are called linear functions. So this is a linear model. We're to answer these questions. You know what to do. Let's see how you did. So when we graph them, we see that they don't fall exactly on the line, but the line is very close to them. So that is the graph that they've asked you to produce. That's what you should have come up with. The projected bank revenue from fees in 2010 was, we use 6, and notice that we're extrapolating here. We're going beyond the data that we have, but we're projecting that it's going to be, when we substitute that into the model, $40.26 billion. Again, the units matter. And the rate of increase of the bank's revenue from overdraft fees over the period is the slope of the line, and it is that 2.19 billion per year. Here is another example. This is about global warming. We have data beginning in 1958 and running through 2010 at various intervals. And this is giving the average amount of carbon dioxide measured in parts per million volume in the atmosphere. So that's the data. We do a scatter plot those points. We get a picture that looks like this. And we model these using this model here. Now, functions such as this are called quadratic functions, or polynomials of degree 2, because the highest power of t is 2. And there's a lot of numbers there, and this runs from 1 to 53. So that is the curve fit. Here's what you're supposed to do. Use the model to estimate the average amount of CO2 in 1980, and assume the trend continues. Use the model to predict what happens in 2013. You know what to do. Let's see how you did. So you're plugging 23, because that's what 1980 corresponds to, into the model that we have, and you round that off to 338 parts per million volume. And 2013 is going to be 56. We plug 56 into the expression. Do the calculation. You will be using calculators, but you'll be using the calculators that are on the PC, and you'll get 395 parts per million volume. This example deals with the Social Security Trust Fund assets, and it shows what are the assets that the fund has over years. So we draw a scatter plot of that data and we do a curve fit. Now this curve fit involves t raised to the fourth power, where t equals 0 corresponds to 2010. This function is called a quartic or a fourth degree polynomial, and you're to use this model from 0 to 27 to answer these questions. And the source of this information is from the government, the Social Security Administration. You know what to do. Let's see how you did. So the assets of the fund in 2011, when t equal 1, you plug t equal 1 in there, do the calculation, and you will get $2.82 trillion. And they ask you to do it in 2029, and you'll get $3.46 trillion. And when you look at the graph, you will see that they run out of money in 2037. Many of you will be alive in 2037, so you really are interested in this problem very significantly. Probably even more than I am interested in this problem. Here's the next example. It's about driving costs, and this is miles per year, and this is cost per mile, and this is in cents. And so we do a model based on this information, and this is the model that we come up with. Now this is an example of a rational function. There's a numerator and a denominator, and the exponent in the denominator is not an integer. It's kind of a complicated thing. And it says x is miles per thousand, thousands of miles. And so we're going to use a scatter plot, and what we're supposed to do is use this model to estimate the average cost of driving a 2008 medium-sized sedan, $8,000 a year and $18,000 a year. You know what to do. Let's see how you did. So there's your model, there's the scatter plot, there's the graph of this curve. So you're plugging 8 in, because 8 corresponds to 8,000 miles per year, and you get 87.1 or 87.1 cents per mile. If you go 18,000 miles, you plug in 18 and you get that. Make sure you know how to get 18 raised to the 1.72 in your calculator, but here it's going to be 50.6 cents per mile. We are going to be talking about some economic models. A demand function expresses the relationship between a unit price and the quantity demanded. You see, the higher the price, the lower the demand. The lower the price, the higher demand. So a demand curve looks like this. Conversely, a supply curve looks like this. The higher the price, the more people are trying to make it and competing. So this is a supply curve. This one tends to get lower. This one tends to get higher as the price increases. So we have demand curves and we have supply curves. Whenever these are commodities, and that's all, what these apply to, what will happen is there will be a point called market equilibrium where the red curve, the supply curve, is equal to the blue curve, the demand curve, and that's called market equilibrium. So there is a point x0, p0, which is going to be the equilibrium quantity and the equilibrium price. Here's an example, and this is a demand for some headsets. And so there is the demand function, and here's the supply function. Now P is expressed in dollars here, and X is expressed in units of 1,000. Find the equilibrium quantity and price. You know what to do. Let's see how you did. So what we have to do is we have to solve these two equations. Now they're both equal to p, so we can set them equal to each other. So we will set this one equal to this one, and we will solve. Now this ends up being, we're going to get everything on one side, set it equal to 0, so this is what we get when we have that. And it turns out that this is going to factor, and we find out that x is equal to minus 400 rather, over 9, or x equal 20. Now x must be non-negative because there's demand, so we're going to reject this root. The math was good, but it doesn't fit the model. Therefore, the equilibrium quantity is 20,000 headsets. And then the equilibrium price is found by substituting the 20 into the model that gives you the price, and we substitute it here, we get 40. So these two things cross at 20, comma 40. So the equilibrium price is 40, and the equilibrium demand is 20,000. Here you have to actually formulate the model. A guy's building a fence. He has only so much fence to use. He has 3,000 yards of fencing. He wants to build the biggest area that he can. And so in one side he's got a river running fast, and so they're saying that he doesn't need to fence that part. So how big of a area can he do? And so you want to find a function in the variable x giving the area of the grazing line land enclosed by the fence if she, the farmer, uses all of the fencing. You know what to do. Let's see how you did. Okay, so there are two sides that are called x, the other side that's called y, but if I add them together I get 3,000. That means that y, solving for that, is 3,000 minus 2x. So the area is x times y, so it's going to be x times y, but we found that y was 3,000 minus 2x, so this is what we get. Now, the domain, we realize we're going to observe that both x and y must be non-negative, so we say, well, we have to have a fence at all, we have to have x bigger than 0, and I think I would say strictly bigger than 0, and it has to be less than that in order for y to remain positive. Here's another example where we're finding the model. If exactly 200 people sign up for a charter flight, the agency will charge $300 per person. However, if more than 200 sign up for the flight, and we're assuming that's the case, then each fare is reduced by $1 for each additional person. Let's let x be the number of people above 2,000. You want to find the revenue realized by the company. You know what to do. Let's see how you did. Okay, so the number of people times the price they pay, and so what happens is the revenue will be, each person will pay 300 minus x, where x is the number of passengers. So there's the amount they pay, and the number of passengers is this. So the number of passengers times the price per passenger gives you the revenue, and we get this expression. Now clearly this must be non-negative, and that means that x is between 0 and 300. Actually, we're assuming that people are going on this flight, so x is bigger than 0, and it has to be strictly less than 300, because if it was actually 300, you would giving them the price. The price of flight would be 0, or you would be giving it away. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.